Greetings, my name is Matthew, and in this video I'm going to talk to you about verifying trigonometric identities. This is a video about solving puzzles that involve trig functions. If you can't think of anything more fun than that, I don't blame you. I'm not surprised at all. This is going to be good. We're going to start with some easy stuff. We're going to work our way up to some more difficult stuff, and the first thing we're going to do is review some of the identities that we know that we're going to use to solve these problems. Let's have a look. First, we have the reciprocal identities, and those we use very frequently. My guess is these are not going to surprise you. For example, the reciprocal of the sine function, 1 over sine theta is equal to cosecant of theta. 1 over cosine of theta is equal to secant of theta. And 1 over the tangent function is equal to cotangent. And I could definitely go through and take the reciprocal of both sides of all three of those equations, and we would have another 3 reciprocal identities, or at least the reciprocal of 3 existing reciprocal identities. I'm going to stop saying reciprocal now. We also have the quotient identities. There's really only one primary one that we look at, and then you could also take into account its reciprocal. Darn it, I said reciprocal again. And the primary quotient identity is that the sine divided by cosine of an angle measure is equal to tangent. Take the reciprocal of the left-hand side, you must take the reciprocal of the right-hand side. Left-hand side becomes cosine over sine. Right-hand side becomes cotan. And are you going to say hello or just climb around? Come say hello before you go and break something. You remember our little friend Sophie. Sophie's been under the weather for, the better part of a week. Why are you looking down? Your fans are awaiting you up here. Do I have to tip you all the way? How do we get... Look at those arms sticking out. You're a goof. Go climb around somewhere other than on the iPad. She had a bad head cold, and we just had to kind of wait it out. She slept a whole bunch and ate a little bit, but not very much, and today she's been chasing Luna around pretty good, so I think she's finally taken a turn for the better. But you're not here to find out about the health of Sophie. You want to know more than anything about the Pythagorean identities, or at least to be reminded what they are. And there's the primary one that says sine squared theta plus cosine squared theta is equal to 1. And then there are 2 other versions of this where we take the entire equation and we divide it by sine squared, which gives us 1 plus cotangent squared theta equals cosecant squared theta. Or we could take this equation and divide the entire thing by cosine squared. Then sine squared over cosine squared equals tan squared plus 1 equals secant squared theta. So those are your Pythagorean identities. I don't ever memorize all 3 of them. I memorize the first one, and then I know how to derive the other 2, dividing the entire equation by either sine squared or cosine squared. Even and odd identities. Remember that the tangent and cotangent functions are your odd trig functions. And when you have an odd function, I'll use tangent, for example, instead of doing it in terms of f of x. The tangent of negative theta is equal to the opposite of the tangent of positive theta. It looks like we factored the negative out of the function. That's not really what happened here. We're just sort of noticing a pattern. So this is true. This kind of a relationship is true for odd functions. I guess I should write odd over here maybe. And then for even functions, which are the other 4 functions. My handwriting failed even more than usual just then. There we go. For even functions like cosine, for example. Did I say that wrong? I'm doubting myself now. I did say that wrong. I don't know what I was thinking about. Maybe the periods of the functions, pi versus 2 pi. Tangent is an odd function, so is cotan. Sine and cosecant are also odd functions. It's cosine that is the even trig function along with its reciprocal function, secant. So cosine and secant are your even functions. The cosine of negative theta is equal to the cosine of positive theta. It's not that we're factoring the negative out, it's that the negative sign looks like it kind of disappears. Cofunction identities, there's no way I'm writing all of these out because they're kind of long and kind of irritating, and I feel like I don't use them all that often. In fact, I use them so infrequently that I typically have to go look them up again. I can't memorize everything. The sine of 90 degrees minus some angle measure theta is equivalent to the cosine, which is sine's co-function. It's equal to the cosine of theta. The secant of 90 degrees, or pi over 2 radians, minus an angle measure theta is equivalent to secant's co-function is cosecant. No surprise there. Of theta and tangent, same spiel. Pi over 2 minus theta is equal to cotangent of theta. You could take, let me fix my highlighter here. You could take this and have it trade places with this, and the statement would still be true. Same goes for here and here could be swapped, here and here. Those arguments could be swapped, and those 3 statements could be written yet again, turning 3 statements into 6. You might need to use variations of the above identities. Indeed, I've mentioned some of them without writing them out. So either write them out or go back into your notes and rediscover them where you wrote them down for the first time. And then here is, and by here I mean here, I thought that was still a highlighter. Here is a rule that I abide by that is not necessarily held to as strictly as I'm going to adhere to it. But if you can see right at the bottom of the screen, it says verify the identity, blah, blah, blah equals blah, blah. Doesn't really matter what it is. My point is that I'm going to pick one side of that equation to modify, and I'm not going to touch the other side. Ever. There's no substitution, there's no adding or subtracting anything to both sides or anything like that. I'm only going to adjust one side of the equation. You'll see these identities proved other ways if you're one of my students, and this ends up turning into a free response question where I have you verify a trig identity, maybe on a quiz or as a free response question on a test. I'm going to want you to do it my way, but be aware that there are other approaches. So let me show you how I would tackle this first one. Typically, my strategy is to choose the more complex looking side of the equation and try to simplify it so that it ends up looking like the other side of the equation. So I would say in this case that the left-hand side is more complex looking. Now I've done these problems a bunch of times, but I haven't done them recently. You know, it's been like, I don't know, 6 months or whatever since I've done this specific problem. So I'm talking through these sort of as though I've done them for the first time, but I know my building blocks really well. I know that cotan is an odd function, so I can factor the negative out. I know that cotan is the reciprocal of the tangent function. So I'm going to talk a lot of these things out, and that will hopefully educate you to an actual thought process that you can be going through as you're sort of rooting around in these problems, because you could go down path A or path B and choose the wrong path for sure, and you're going to end up just crossing some of this stuff out and starting from scratch. So if that happens, don't be surprised. I have filled 3/4 of a page worth of work on a problem like this, excuse me, and it was wrong. And I ended up bracketing and throwing away about 70% of that work and I didn't go back to square one, but I did have to go back and almost take it from the top. So that can happen. Okay, so enough talk, more writing. The cotangent is an odd function, so maybe I'll put a little note over here that says odd, and that's what's allowing me to take that negative sign out and write this as the cotangent of positive x. And then there's the sine x still. Why did I do that? So I'm allowed to do it because it's an odd function. Why did I do it? Because the argument here is negative and the argument here is positive. Here it's positive also. But I'm looking for consistency in the argument, and so I'd like to get rid of that negative sign. The next thing I'll do is, sometimes I don't know what to do, and I just ask myself, well, what do I know that I'm allowed to change? And I know that I'm allowed to change cotangent. It's the reciprocal of the tangent function, and tangent actually is sine over cosine. So I'm going to write cotan as cosine over sine, and then we still have to multiply this by this sine x. Oh yeah. See what happened just there? So in order to go from my first handwritten line to my second handwritten line, in order to go from here to here, I used a it's the reciprocal of a quotient identity. I'll let you write that in here. Reciprocal of a quotient identity. You should write out the actual words. Roki? I like that. Okay. And then all we have to do is simplify. That's pretty obvious. I like to circle things that are canceling out, and then you'll notice that the left-hand side clearly equals the right-hand side. If you want to write it down that the negative cosine of x equals the negative cosine of x, that's fine. And then sort of as a mathematical punctuation mark, I'm going to draw a little box and kind of shade it in. And let me see if I can find an example of that for you. Apparently I need to find an older version of a textbook. I'm here in Stewart's calculus book, and what I'm finding, and this is like actively an ebook, so I can't circle anything like I normally do because this is not a PDF. But if you look, well, how can I do that? Oh, I could do this. Maybe? Nope. Darn it. I need to figure out how to do that. Okay, this is ridiculous. Now there are two of me, but the right-hand one of me that's clearly on my webcam, I'm pointing at these three green dots right here, and also, yep, those three green dots that you're seeing right there. So those are, I've got to get rid of this other version of me. Get out of there. What those are these kind of mathematical punctuation marks that I was mentioning. It's not the square box that's shaded in. The other mathematical punctuation mark at the end of a proof that we see sometimes says QED, which is short for Quod Erat Demonstrandum, which is Latin for it has been shown. So at the end of this proof, above the first set of green dots, it says, by working with the left side and arriving at the right side, the identity is verified. And below that, above the next set of green dots, it says, thus, the identity is verified. So it sort of harkens back to kind of an old school way of wrapping up a proof. Where were we? Here. Well, that was pretty smooth. That was almost like I knew what I was doing. Let's check out another identity. I don't know if one side of this equation is more complex than the other. I don't know, let's try messing with the left-hand side. What am I going to do to the left-hand side? I don't know. I'm just going to change something. I'm going to follow the rules of the identities that are available, and I'm going to change something. So I think I'll change tangent into... Oh, I have to re-enable my pen. All right, so tangent is sine theta divided by cosine theta. plus cotangent. Cotangent is cosine theta over sine theta. So those were two versions of the quotient identity. I could write identity at the end of all of these. All of these are going to be identities. Well, a lot of them anyway. What are we going to do next? The right-hand side is all kind of smashed together and attached by multiplication. Maybe if I make a common denominator. I don't know. Let's try it. I'll take the first fraction and multiply it by sine over sine. And then plus, and I'll multiply the second fraction by cosine theta over cosine theta. And remember that I'm allowed to multiply by sine over sine or cosine over cosine because those two fractions are equal to 1. So what we're really multiplying by is 1. So we're not changing the value of anything, we're just changing what it looks like. Now my first numerator is sine times sine, which is sine squared theta. And plus, my second numerator is now cosine squared theta. And yes, sine squared really is shorthand for sine theta, in parentheses, squared. So sine times sine makes sine squared. All right, and that's all over our common denominator of sine theta cosine theta. I'm still hoping that this is going to turn out to equal the right-hand side. I'm seeing some good things because secant is 1 over cosine and cosecant is 1 over sine, and those things I have in my denominator now, so that's good. I need my numerator to be a 1. Oh, guess what sine squared plus cosine squared equals? By the Pythagorean identity, it's equal to 1. So all we did in our second step was make a common denominator. And now we're going to pull the trigger on the Pythagorean identity. And write the left-hand side as 1 over sine theta cosine theta. If I were grading your test or quiz, I would know that this left-hand side does pretty clearly equal the right-hand side. You have to know to your audience, though. If you're writing this proof for a professor and you've gotten it like pretty much one step away from the left-hand side being identical to the right-hand side, you can stop. If you were trying to demonstrate this for a fellow classmate and make it really clear to them that the left-hand side does equal the right-hand side, I might rewrite this one more time as 1 over cosine theta times 1 over sine theta equals, and now it should be really clear that 1 over cosine equals secant on the right-hand side, and the 1 over sine theta equals the cosecant on the right-hand side. And then you could put your little box here and shade it in. That's what I would like my students to do. You could put, I suppose, 3 larger dots, although I've never seen that before, and really that's what you click on if you want additional options in a menu system, so I won't be using that. You could write QED if you want to. I'm going with the box, though. I don't know, which side do you think is the more complex side? Right, so no big reach here. But what am I going to do on the left-hand side? Again, I've seen these before, but be mindful of these initial strategies that we're using in order to pick these apart, because those are the processes that you're going to bring to bear on new problems. So the left-hand side here, something that I see is that both of the terms contain a factor of cosecant x. So I'm going to factor. I'm going to factor out the GCF, the greatest common factor, which is cosecant x, which leaves me with a 1 minus a cosine squared x equals. Now 1 minus cosine squared x. it's got a cosine squared and a 1 in it, which makes me want it to somehow be related to the Pythagorean identity. I'm going to switch colors and write myself a little note up here that says sine squared theta, or x, plus cosine squared theta equals 1. Can I make that statement say 1 minus cosine squared? I can. All I have to do is subtract cosine squared from both sides, which leaves sine squared all alone on the left-hand side. The right-hand side becomes 1 minus cosine squared. And all of a sudden, this is very useful because it's the same as this. So we'll do substitution, definitely using the Pythagorean identity. Pythagorean. Replacing that with a sine squared. So now I've got cosecant x times sine squared x. I'm getting sloppy. Squared x, there we go. Hopefully is equal to sine x. Now what am I supposed to do? I'm telling you, just keep changing things into other things while still following the rules. I know that cosecant is the reciprocal of, oh yeah, that's nice. When you see it, when you finally see it, it's kind of satisfying. Cosecant is 1 over sine x times sine squared x, or you could write it as sine x times sine x, or you could write it as sine x quantity squared if you want to. I think it's most typical, however, that you'll still see it as sine squared x equals, and then you can do a bit of reducing here so that all you're left with is sine x equals the right-hand side, sine x. I left out a note about a step that we did when I changed cosecant x into 1 over sine x. That's a reciprocal identity. And then if you want to write simplify or reduce, you could. It has been shown that the left side equals the right side. And that was just page 2 of 6. Could these get more complicated? Absolutely. Could they look more complicated and not necessarily take all that much longer to solve? Also, absolutely. Such is the case in this you try it example. Both sides look pretty similar in complexity, but what I'm noticing is that on the left-hand side, there's a sine squared. Let's wait for it to come back. I think it was a sine squared and a cosine squared. Yep. And the right-hand side only has cosine squared. So maybe on the left-hand side, we can change sine squared into cosine squared. If only I knew something that sine squared was equal to in terms of cosine squared. Where would I find something like that? So we're going to use that modified version of the Pythagorean identity in order to change on the left-hand side sine squared into 1 minus cosine squared. Let's see what happens. So I'm going to keep this cosine squared x minus, and then parentheses, because what we're substituting in place of sine squared has 2 terms. So we want to make sure that the signs work out okay. And this is going to be 1 minus cosine squared x. Hopefully still equals the right-hand side. That was modified Pythagorean identity. Let's distribute the negative, dist for distribute. So we have cosine squared x minus 1 plus cosine squared x equals, that's it, we're done. Cosine squared plus cosine squared is 2 cosine squared. The minus 1 is the minus 1. We are done. You could put combined like terms, I guess, on the right-hand side, but Anybody who knows how to do addition and combine like terms can probably see that the left-hand side now equals the right-hand side. So we're in good shape. Nice job. Let's see, do I want to do all of these with you? Some of these I might want to save for the classroom. Oh, that's great. That's the one that I'll save. I'll give that as a quiz question. What else do we have? Look at it. There was a full page worth of space available to do that one. This one also, full page of space available. Yikes. And then we change gears a little bit and try to disprove some of these suggested identities. All right. Let's see. This one I'll tell you. This one's true, right? The left-hand side does end up equaling the right-hand side. I'm going to let you try this one on your own, and if you're one of my students and we end up doing this one in class, great. But what do you think you should do in this problem? I'm not going to change sine or cosine into something else, but look what you've got. You've got a fraction plus a fraction. Have we ever seen a scenario where we had to add two fractions together? I think we have. And what did we do? We created a common denominator. Guess what you should consider doing in this problem? You should probably consider creating a common denominator. I'm not going to say anything more than that. Do that, find the common denominator, see how it pans out. Left-hand side everything should cancel out and turn into a 0. Maybe we should spend our time together looking at this one. This one looks a little rough. The good news is that on the left-hand side of this equation, I can clearly see some things that can change very easily into other things. Cotangent, we know, is cosine over sine. On the right-hand side of this equation, I wouldn't even know where to begin. So I'm going to cross my fingers, that the left-hand side of this thing turns into the right-hand side. I'm going to left justify my work just in case I have to really kind of blow this thing up. So cotan x is equal to, I've made a mistake already, here we go, cosine x over sine x, and then plus cotan y is cosine y over sine y. A lot of opportunities to make silly mistakes here, so make sure you're writing pretty clearly, that your x's look like x's, your y's look like y's. And in the denominator, here's where I think it's going to get a little crazy. We have 1 minus cosine x over sine x times cosine y over sine y. Now those two fractions can be multiplied together and we could write them as cosine x, cosine y, all together in one numerator over sine x, sine y. And I told you to be writing clearly, and I am not writing very clearly. Let's make sure that looks like a sine x. There we go. So if that's one fraction, then what am I going to do with it? Well, I could turn this number 1 into a fraction that has this as the denominator, and I think I might end up doing that. And in my, what I'll call my big numerator, I could create a common denominator up there. This is going to be a labor-intensive process. Let's just try to stay organized, keep our pencil sharp, and see how it plays out. So in my big numerator, and again, this is what I'm calling my big numerator, let's make a common denominator. I'm going to multiply my first fraction by sine y over sine y. I didn't actually put the little multiplication symbol here and write this as two separate fractions. I just already multiplied them together. You know yourself better than I do. If you need to write those as two separate fractions, or if perhaps you want to write the sine y over sine y in a different color so that it's clearly the new entry into that line. And sine over y, or sine y over sine y is equal to 1. That's why we're allowed to do it. You know, make these notes your own. The second fraction, I'm going to multiply by sine x over sine x. So I think I'll put that first, actually. Sine x over sine x, and then we already had a cosine y over sine y. And those fractions are getting multiplied together, so we'll write them as one fraction. The next time we see those, we'll put them over their common denominator with the plus sign in between them. So that's the big numerator, the big N. In the denominator, I'm going to take the number 1 here, and if you want to, again, use highlighters or different pen colors, not a bad idea. I'm going to change that number 1 into sine x sine y over sine x sine y. Oop, that was a little crazy. Over sine x sine y minus. Now I'm rewriting these things that are next to me here. It says minus cosine x over sine x times cosine y over sine y. I'm just going to rewrite those as one fraction. Cosine x cosine y over sine x sine y. Now if you want, you could come back up here and label this as your big denominator. Come on now. There we go. And then this is still the big denominator. Part of the organizational process. You know, you should be skipping a line in here. And then we'll skip a line right here to make sure that this is as easy to read as possible. I'm going to put my equal sign over here to the right. And now let's write the big numerator as one fraction and the big denominator as one fraction. Even if you can see where this is going, it's not a bad idea to show our work. So I've got sine y cosine x plus sine x cosine y, all divided by the common denominator of the big numerator, which is sine y sine x, and then that's all divided by, and let's bracket it, that's the big numerator. In the denominator, we will write these two numerators separated by a minus sign, all divided by their common denominator. So we have sine x sine y minus cosine x cosine y, all divided by the common denominator of the big denominator, which is sine x sine y. Big denominator, whole fraction equals, hopefully equals the right-hand side. In the numerator we have a fraction, in the denominator we have a fraction. So we have a fraction being divided by a fraction. If you would like to write out the keep, change, flip process, you may. It's going to take, you know, most of the width of the piece of paper, but that's totally fine. If you do that, remember that this fraction gets flipped, which means that the sine x sine y is going to appear in the numerator when you flip it. It'll cancel out with this sine x sine y that's in the denominator. And the result will be that these two will cancel out, leaving us with sine y cosine x plus sine x cosine y, all divided by the big denominator's numerator, sine x sine y minus cosine x cosine y. And my hope is, I wasn't looking, I haven't cheated. My hope is that that's the same as the right-hand side. Let's sort of check them off as we go. I see a sine y here, and then up at the top of the screen, I see a sine y. Next to it is a cosine x. Let's go back to the bottom. Yep, there's the cosine x. Plus, sine x cosine y. Up at the top, sine x, cosine y. Those were even in the same order. At the top of the screen, in the denominator, sine x, sine y. Bottom left, sine x, sine y. Bottom left, cosine x, cosine y. Top right, cosine x, cosine y. We got them. 3/4 of it was even written in the exact same order. It was just the sine y cosine x that had been flip-flopped, but of course a times b is equal to b times a, so we're good. That was a heck of a problem. I do recommend using some kind of alternate pen color or highlighter or, I don't know, whatever kind of additional notation that you can throw in to help your eye follow the thought process. There aren't really so many identities that we used in order to solve this problem. This was predominantly about creating common denominators, and which enabled us to put some fractions together. And then once we had the big numerator fraction and the big denominator fraction situated, we were able to do keep, change, flip, cancel a couple of things out, and we were done. Put a big old QED box down there. All right, nicely done. These are all great problems for you to write down on a separate piece of paper and attempt again later. I'm going to skip over that problem that was on page 5 so that I can work that one perhaps with my students again later. No way, it's a fraction minus a fraction. What do you think you might want to do in order to solve that problem? I would strongly consider making a common denominator. Do I want to make the common denominator on the left-hand side right away? Because it might be tough. There's a cotan on the left and a tan in the denominator on the right. Should I do something else first? You could sure try. I think it's a great idea. You might want to write this as cosine theta over sine theta. And you could write this as sine theta over cosine theta. And then you would need to change this number 1 into something that has a sine theta as a denominator. And you'll change this 1 into a fraction that has cosine theta in the denominator, so that you can be actually doing the subtraction and tidying up those denominators. Once you've done that, you might even want to do a keep, change, flip. And I can't say for sure whether or not this is going to be helpful to you, but remember that a squared minus b squared factors to equal a plus b times a minus b. That's a difference of squares. I don't know if it's going to help you, but just glancing at it, I think it might. All right, so try that one out. The left-hand side should end up equaling the right-hand side if you do it correctly. And then let's look at this little subtopic down here at the bottom. This is asking us to determine whether each statement below is true or false. And in order to disprove an identity, all we have to do is find one input value, or in this case, one x value, that causes the left-hand side to not equal the right-hand side. This is asking us to find 3 counterexamples, but if you've ever been in a relationship where there was reason to not trust the other person, do you really give them 3 attempts? 2 maybe, but the second one pretty much seals the deal. I don't have to disprove this thing 3 times. I'm just going to try to find one x value that makes it not true. An x value of 0, if I plug that into this equation, I would end up with the sine of 0. 2 times the sine of 0 equals the sine of 0. Maybe that would be helpful, except that the sine of 0 is 0. So now I've got 2 times 0 equals 0. And that's a true statement, so that didn't help me any. So if you want to write that out and illustrate for yourself an example of what not to plug into the equation, it's not that you shouldn't plug in 0, it's that we plugged in an x value of 0 and it wasn't helpful. The left-hand side still equaled the right-hand side. Now I'm going to try a different x value. Let's say maybe x equals, I don't know, I'm thinking pi over 12? Maybe I'm crazy. Definitely I'm crazy. Let's try it. We have 2 times the sine of 3 times pi over 12 supposedly equals, question mark, the sine of 6 times pi over 12. Let's see if this turns out to be true. On the left-hand side, we've got 2 times the sine of, the 3 and the 12 reduce, leaving us with a pi over 4. On the right-hand side, the 6 and the 12 reduce, leaving us with the sine of pi over 2. And then let's evaluate these trig functions. On the left-hand side, we have 2 times, and the sine of pi over 4 is root 2 over 2. On the right-hand side of the equation, the sine of pi over 2 is equal to 1. On the left-hand side, these 2's are going to cancel out, leaving us with a statement that says the square root of 2 is equal to 1. I don't think so. Therefore, what does it say? Explain why the statement is not true. It's not true because because the square root of 2 doesn't equal 1. So you can write whatever you want here. Therefore, original statement is false. Original statement is not an identity. Either one of those would be good. So you get the idea. You have to plug in x values and try them out and see what you get. Here you could try 0 again, except you're going to get 0 plus 0 equals 0. So not a good idea. You could try maybe pi over 2. That would be a good one. You know how to figure out the sine of pi over 2 and the sine of pi over 2. And then this is going to turn out to be the sine of pi. You know, try it out. See how it plays out. If it doesn't work, you'll have to pick a different x value. And that's it. That is the end of this set of notes where we're looking at proving trigonometric identities. I hope that was a good review of some of the existing identities that we already knew, and we got to apply them in a different way. If you'd like, just below me should be a link to the next video in this series. Check that out, especially if you're one of my students, because you've got more work ahead of you. And if you're not one of my students and you like what I do, come back and join me. Like and subscribe, and hopefully I'll see you again. Thanks so much.